Hi everyone, I'm Sudheesh. I'm a PhD candidate in computer science and engineering at the University of Washington. And today I'll be presenting a small part of my thesis work on distributing trust in computing infrastructure. So in my thesis work, I focus on three functional pieces of the internet. So there is the access layer, which is your 4G, LTE, 5G, satellite. And then there is the connectivity layer, which most of you in this room are fully aware of. And then there are the applications that users like to interact with. But today, I'll focus only on one small part, which is focused on some of the networking protocols around connectivity. So there's a large number of nation-scale network operators who handle and control a majority of the internet traffic today. And users also interact with, there we go, yeah. And users also interact with a lot of these services, either knowingly or unknowingly, and place a lot of trust in them. For example, DNS or the routers that they're sending their traffic through. And while my thesis work focuses on the different infrastructure components that build the internet, today I'll focus on DNS and its ripple effects on page load time and page load events. So as most of you are aware, DNS protocol is clear text, and it continues to be the most widely used by clients all across the internet today. And the protocol is known to be vulnerable to network adversaries who would like to monitor, eavesdrop, and also tamper some of the connections. So this opens up a lot of challenges for privacy. And the resolver, the emergence of these protocols like DNS over HTTPS or DNS over TLS address some of these challenges by creating a secure transport channel between the client and the resolver. But this is not really enough, because while it protects us from network adversaries, it opens up challenges for privacy. So why does this happen? The reason is the resolver responding to the client knows exactly who the client is and the underlying information of the query that the client is making, but they can use this information to profile the client. Even for privacy-aware resolvers out there, which operate as non-logging resolvers, or might have privacy policies in place indicating that they would like to delete client information every 24 hours or periodically, there might be technical mechanisms which are much more valuable and desired by these resolver operators. So this is exactly what we do with Oblivious DNS over HTTPS, or ODO, a part of my work during my internship with the folks at Cloudflare Research. And ODO builds on top of the existing DOE standards, and it includes this architectural decision to include a proxy in the middle. And the assumption is that the proxy and the resolvers are non-colluding. Now, through the usage of hybrid public key encryption, we can overcome some of the cryptographic overheads and minimize them. But the proxy is put in place so that the proxy knows information about the client, but has no information about the query or the response that it gets back. And the resolver has the information about the query and can create the answer as they can do today, but has no information about what the client is. And this split in the kind of data that we expose to different parties kind of helps us improve the privacy. But of course, I mean, there is no free lunch. So most of you might be wondering what happens to performance. And the performance for usage of ODO is a little bit worse than that of using DNS over HTTPS, but these are not due to the cryptographic overheads, but rather because of network path characteristics that exist. But at the same time, if we strongly agree with the assumption of non-collusion, they provide the same security and privacy guarantees as that of DNS over HTTPS over Tor, or using anonymous DNS script. Now, the next immediate question that comes to mind is, what happens to the page load time experiences when we're using secure protocols like this? And what we found out by scanning the top 500,000 websites in the world is most of the times we reach the same set of networks for receiving access to resources. And most web pages, despite the fact that they are sharded by hostname, continue to be provided by a small number of network operators out there. So can we leverage this co-location of information and co-location of resources to do something interesting for performance and also for privacy? So what you see here in this example is a standard workflow that is used by browsers where as a browser, I go to example.com, I receive a set of IP addresses, I choose one of the IP address, make a TCP and a TLS handshake, and then identify that I need a sub-resource for CDN.js, which may be hosted by the same service provider, but the return IP addresses for the subquery for CDN.js might be a different set of IP addresses because of DNS load balancing. In this case, we can't reuse the existing TCP connection or the underlying TLS connection in any way, and we're forced to create a new TCP and TLS handshake. By using authoritative origin frames, which is the HTTP origin frame standard, and extending the certificates as the service provider by improving it and including CDN.js in the SAN attributes of the certificate, we can now send an additional hint from the server side to the clients telling, hey, you can ask us for information about CDN.js. Go ahead and reuse your connection. And this prevents additional DNS and TLS handshakes. But does this actually work in practice? Or what does the impact of this even look like? So when we ran a bunch of measurements, we realized that using this mechanism could save us over 60% of redundant DNS and TLS connections that we make today. And we deployed this in production with 5,000 websites, and we realized that the same servers now receive 50% lesser TLS connections for those websites, allowing us to repurpose the same servers to more clients. And these are not, these also reduce the amount of cryptographic overheads that clients need to incur and also the servers need to incur. But the most important bit of it all is that every coalesced connection reduces the availability or reduces the ability for network adversaries to fingerprint what could have been otherwise plain text SNI information in the TLS handshake. So this improves client privacy. But one of the things I would like to ask the Nanog audience here is for suggestions. As we look forward, we see this architecture where we're starting to trust either the resolver or in case of RPKI, we trust the RIR to sign and maintain these records correctly. Is there an incentive to use things like DNSSEC and reduce the amount of trust that we as clients might be placing on such infrastructure? But the benefits of DNSSEC and things like this cannot be provided until the entire hierarchy has DNSSEC. So if you see the map there, the red color sections are the TLDs, which still don't support DNSSEC. So what can we do as a community to provide an incentive for improving DNSSEC and similarly reduce the amount of trust that we place in the RIR ecosystem for RPKI when we look at BGP? So this is just a small slice of the overall work that I'm doing, and I would love to talk to more people about this. And that said, the two papers that are listed here are the works that I presented today. And I will be graduating soon, and I'm looking for new full-time opportunities in research and engineering. So thank you.